The Millennium Bridge, a familiar sight whose stylish design proved to be critically flawed when it was first opened to the public back in June 2000. Nearly 100,000 people stepped onto the structure, but immediately it was obvious that something was wrong. Small oscillations in the bridge's structure quickly intensified into swaying motions, and the bridge was closed the same day to prevent injury. But why did this happen? The natural sway in the pedestrian's walk provided small sideways oscillations, causing the bridge to wobble. The people on the bridge stepped into these vibrations to regain their balance, creating a positive feedback cycle and amplifying the swaying motion. To fix this problem, engineers fitted various dampers along the length of the bridge, for example, fluid viscous dampers. This device consists of a piston that moves from side to side. The amplitude of the oscillations is reduced by having hydraulic fluid flow between different sized chambers through an opening, dissipating the energy of the vibrations through heat. So, now that we know the importance of damping, let's get on to the theory.
Let's apply some mathematics and physics to the concepts which you have just been introduced to. So this is a spring. You can see it's a damped harmonic oscillator. It goes up and down and then it wiggles a bit. If we measure the displacement of this point with the horizontal, we call it x. Physics tells us that there is a resulting restoring force when I push it down, which we can model with minus kx. A friction force, which is due to the interaction of the atoms between each other, which dissipates in heat, which we can call c or lambda dx by dt, so speed. And Newton's second law tells us that this is equal to ma, or acceleration, or the second derivative with respect to time. So we can introduce some variables here to help us along the way. We can introduce omega 0 squared, which is k over m, and 2 gamma, which is equal to lambda over m. So we can see that this is sort of like a quadratic equation, except instead of variables we have a derivative. So we have second derivative first and 0.
Then we have r1 or 2 is equal to minus gamma squared plus or minus square root of m squared minus omega 0 squared. And so since we have as a factorization of this, of the derivatives as a quadratic, we end up with a expression of the form d by dt minus r1 or 2 equal to 0. We can see that the solution is going to be a sum of exponentials, since this is what gives a constant result times the function itself once it's derived. So we can deduce that x is equal to a e to the r1t plus b e to the r2t.
So we're going to answer this example question. If x equals e to the t, x dot equals k e to the k t, x double dot equals k squared e to the k t, which gives us a quadratic formula where k equals minus 2 gamma plus minus root 4 gamma squared minus 4 omega naught squared all over 2. So we can simplify this to get two constants. We can get an expression for displacement,
which we can call x of t. We know what gamma is. It's lambda over 2m, which is equal to 0.3 over 2, which is just 0.15.
So we can take a factor of e to the minus 0.15 t out of the original equation,
which gives us our final answer for an expression for displacement in terms of t.
Now it's time to apply the theories into the real world. Otherwise, why does this massive stuff matter? Actually, from the theories we derived before, we can specifically classify the damping phenomenon into 3 levels: light, critical, and heavy damping, in which each of them has wide applications in lives. First, let's go back to the general differential equation for a moment. The 3 cases are distinguished by different forms of its solution. Before, we've demonstrated how we solve light damping, where gamma smaller than omega null give omega be real and positive, range from 0 to omega null. In this case, the Q factor is very large and the solution has a form as shown. Assuming body experiencing light damping, if plotting x against time, we can see the amplitude of motion shows exponential decay with time. Well, it's still doing oscillation. Body takes a long time going back to the equilibrium. These characters are applied in string instrument. An easy example could be a guitar. Let's then look at a case of heavy damping. Here, the gamma is greater than omega null, leading omega be imaginary, and the 2 roots of the original differential equation are wholly real. The displacement is solved as below. where both roots are negative and the absolute value of Q2 is greater than Q1. Now we add the plot of heavy damping in. The amplitude becomes 0 in a shorter time, and there is no oscillation at all. That's why heavy damping edifies damper on door, which enables us to close the door slowly without any oscillation. What if gamma equal to omega null gives omega value of 0? Have we found out the roots are gonna be equal and thus gave a solution in the form of? It finally comes to critical damping, the one with the most various uses in life. If we compare the diagram for critical and the other two together, what have you noticed? Doesn't it seem like the body under critical damping requires the least amount of time reaching the equilibrium, also without any oscillation? Indeed, this property gives wide applications of critical damping, common as car suspension or powerful as turn mass damper.